Today, we study Coulomb's law. We first consider the electric charge. And any matter is composed of molecules. Sure, there exists a matter which does not consist of molecules, but most cases molecules. In molecules, a molecule consists of atoms. An atom is composed of a nucleus and electrons. Nucleus and electrons. And if you look inside the nucleus, you'll find protons and neutrons. We'll find that the proton has a charge plus E, that's a positive. Electron has an electric charge minus E, that is negative. And neutron is neutral, electrically neutral. In fact, protons and neutrons are all hadrons. Any hadron is composed of quarks. There are up, down, charm, strange, top, and bottom. There are 6 kinds of quarks. B. Electromagnetic force governs the bound state between the nucleus and the electron. The electric charge, if there are 2 electric charges, then they communicate each other, they exert the electromagnetic force. And the nucleus is composed of protons and neutrons, and protons are positive charged and electrons are negatively charged. There is some strange point that any electric charge of equal sign repel each other, and any electric charge with different opposite sign attract each other. By applying this Coulomb's law to this nucleus, it is very strange. Protons are all positively charged particles, and neutrons are neutrally charged particles. It is electrically neutral particles. So there is no reason to have nucleus as a stable state. Therefore, electromagnetic force, in addition to the electromagnetic force, there must be a very strong force combining them together. That is called nuclear force. Nuclear force is composed of 2 kinds, strong force and weak force. But we are not so much interested in that advanced material in this class. We focus only on the electromagnetic force. Anyway, any electric charge is positive, negative, or neutral. And any 2 charges of equal sign, plus plus or minus minus, they attract equal sign, repel each other. Equal sign repel each other. Any 2 charges of opposite sign attract each other. Let us consider the helium atom. The symbol of helium is He. This number 4 represents the mass. Mass means in a nucleus there are protons. There are 2 protons and 2 neutrons, and each proton, each neutron has a mass number 1. So helium atom consists of 2 protons and 2 neutrons. So mass number is 4. And this number 2 represents number of protons. So that is atomic number 2. Mass number is 4. So it reads 2 protons repulse each other in view of charge, electric charge. That's correct. The electromagnetic force is not enough to explain the stability of nucleus. I have already explained that nuclear force should exist. The third one, the nuclear force called the strong and weak interactions govern the formation of the nucleus. In view of electrical properties, we consider conductors and insulators. And conductors are materials through which charge can move. Charge can move. Conductors. Opposite to conductors, insulators. Inside insulators, theoretically, charge cannot move. But actually they are composed in a macroscopic scale. The electric charge is statistically do not move, but in a microscopic viewpoint, there are electric charges. They are moving around, but average value as a macroscopic scale is vanishing for the insulators. So conductors are normally the metals. For example, silver, copper, gold, aluminum, and so on. You should be acquainted with all these. Okay? Non-conductors, sometimes it is also called the insulators, and materials through which charge cannot move freely. Another kind in the middle is a semiconductors. There exist semiconductors. Semiconductors is very useful to make electronic devices. And there are superconductors that allows a very large amount of current, because resistivity is vanishingly small. This is the periodic table of elements. There are many elements, and you will find some numbers. This 1, 2, 3, 4, 5. They are the number of protons in a neutron nucleus of a single atom. And these numbers are average value of mass. So this is not an integer. That means there are various elements with the same number of protons but with a different number of neutrons. They are called isotope. So this is a statistical average of those values that can be found on Earth. Next, we consider charging and discharging. If a positive and negative charges are balanced in an object, then the sum of positive charge and negative charge vanishes. That we say neutrally charged. A charged object has an unbalanced positive or unbalanced negative charge. Discharging. That unbalanced either positive or negative charge disappears to make a neutrally charged state. So, return to the neutrally charged state from the unbalanced charge is called the discharging. Connecting an object to the Earth's surface with the conductor is called grounding. Next, we consider Coulomb's law. Basically, Coulomb's law is very similar to gravitational force. First of all, it follows in this way. There is a charge Q1, another charge Q2. There's the origin of a frame of reference. This is a vector connecting the two point charged particles. So R in here is R221. So R1 subtracted by R2. If there are 2 point charges Q1 and Q2 experience the electrostatic force. According to the Newton's third law of action and reaction, we write this one: force applied to particle 2 by 1. This is force applied to particle 1 by 2. Action and reaction states that the sum of the two forces must be the same. That means they are F1 to 2 equals minus F2 to 1. They are equal in magnitude but opposite in direction. The two forces are equal in magnitude and mutually opposite. The force is attractive if the product of the sign, the product of the two charges is negative. The force is repulsive when the product is positive. The force vanishes when the product is 0. So, the strength of the force depends on the product of two charges. If we consider the gravitational force of the 2-point massive particles, only attractive force appears in the gravitational case, because anything massive has mass, positive mass. Okay, that is the big difference between the electrostatic force and the gravitational force. The strength of the electrostatic force is inversely proportional to the distance between the two charged particles. inversely proportional to the distance. More exactly, the strength is proportional to r squared. So it follows the inverse square law. This is the same as the gravitational force. Next, the electrostatic force is similar to the gravitational force, except that the charges are replaced with the masses. Gravitational force is attractive only, but electrostatic force attractive if the product of the charges is negative, repulsive if the product is positive, vanishing if the product either one, so both or either, only a single one is a positive charge that is neutrally charged, but regardless of charge of the other one, it is the electrostatic force vanishes. The SI unit of the charge, electric charge, is Coulomb. The Coulomb unit is derived from the SI unit from ampere. And ampere is the unit for electric current. An electric current is defined by charge per unit time. Therefore, delta Q is I times delta T. This is time, second. SI unit of current is ampere, so 1 ampere is here. So 1 Coulomb is defined by 1 ampere multiplied by 1 second. We combine everything all together to write down the electrostatic force representing the Coulomb's force. Coulomb force applied to charge 1 from charge 2 is like this. Here, the overall coefficient K is called the electrostatic constant. Q1 and Q2 are charge of each particle. And R hat here is Q1, Q2, R1, R2. This is R1 subtracted by R2. And unit vector R hat is the unit vector along the direction from 2 to 1. Okay. So if they are positive, then the force is repulsive. If product Q1, Q2 is negative, then the direction of the force is opposite to make it attractive. You don't have to memorize all these digits, large number of digits, but the electrostatic constant is of order 10 to the 9 Newton meter square divided by Coulomb square. 8.9875517923, and this number in the parentheses represents the error. Uncertainty is less to 2 digits. Here, this epsilon 0 is called permittivity constant. Epsilon 0 is called the permittivity constant, which is defined by the speed of light. Later we will study the Maxwell has found that the product of this permittivity constant, epsilon 0, and vacuum permeability, mu 0, this product is related to the speed of light. Okay. And speed of light, c, is 299,792,458 meter per second. Perhaps you have to memorize all exact number. This is exact. It is not an approximate number. The speed of light is exact number according to the special theory of relativity. The electrostatic force obeys the principle of superposition. So, net electrostatic force applied to particle 1 is the sum of all forces due to other charged particles. So, this is sum over J is not equal to 1. F vector J to 1. Alright, shear theorem. There are two shear theorems. Shear theorem is already known from the gravity, Newton's gravity. It is related to the chart of mass distribution of a spherical mass distribution. For example, a celestial body such as Earth moving around the sun, here's the gravitational force, and the magnitude of that force is exactly the same as the point particle of mass, whose mass is the same as the Earth, and the two particles of Sun's mass and Earth mass, they are of equal gravitational force. So if the mass distribution is distributed symmetrically, spherical symmetrically, then just like this spherical object experiences force, just like all of the masses are concentrated on a single point. Okay, so that is called shear theorem. The shear theorem 1 states that the electrostatic force on a spherically symmetric charge distribution of net charge Q is the same as that for a point charge Q at the center. So this is shear theorem. Shear theorem 2. This is advanced application, and let's read it. A point charge inside the spherically symmetric charge distribution does not experience any electrostatic force. So we have a spherical charge distribution inside the sphere, no electric field, no electrostatic force. Spherically symmetric charge distribution. Once the charge distribution is spherically symmetric, then inside inside that spherically symmetric charge distribution, there is no electrostatic force. Okay, let us consider problem 6. Consider two uniformly charged spheres with charges Q1 and Q2 of radius ARI. So A1 and A2. So they have different radii. A. The electrostatic force between the two spheres is K, Q, and Q2. That's fine. Where R is the distance between the two spheres. Okay, we have two spheres. Center R. This is R, right? So this problem is related to the shear theorem. B. If the two centers coincide with each other, then the electrostatic force between them vanishes. Yes. Spherical charge distribution, they do not feel. According to shear theorem 2, they do not feel the electrostatic force together. And second, yeah, that's it. Spherical symmetric, it is impossible to have electrostatic force between them. Number 7. Two uncharged metal spheres A and B are in contact. Uncharged metal spheres, okay, in contact. So they are electrically neutral. A negatively charged rod is brought close to A. Then what happens? This negatively charged attracts the positive charges. But everything it used to be neutral. So there should be some negative charge. And this negative charge repel those negatively charged particles. Alright? Because of the negatively charged rod, A is positively charged. Correct. Because A and B are in contact with each other, B is negatively charged. Correct. If A is charged with Q, then it should be minus Q, because the sum of this must be zero, because charge must be conserved. D. The two spheres are then slightly separated. A, B. This is a plus and this is minus, and then they have different sign, so they attract each other. Number 8. A positively charged metal sphere A is brought into contact with the uncharged metal sphere. Okay, so these problems are very similar to those. Alright. So simple. Let's consider number 12. Two identical conducting spheres, A and B, carry the common positive charge Q and exert electrostatic forces of magnitude F on each other. They are separated by a distance d much larger than the common diameter d. A this diameter is d, and we have B, this diameter is d, and their separation is capital D, and D is much greater than small d. A third identical conducting sphere, C, is uncharged. So positive charge, common positive charge. So this is Q, this is Q. This is C. C is the first touch to A. C is a third identical conducting sphere, uncharged. So it has a diameter D. So it touches A. When it touches A, because they are identical in diameter and materials are the same, this charge Q must be distributed evenly in the whole system, A plus C. So after touching A and C are charged with half of original value of A's charge. So initially C was uncharged and only A and B are charged with Q, but after the touch between A and C, the charges of A and C becomes 1/2 of Q. Alright, and then C touches A, then to B. So we have now A 1/2 Q, B Q, C 1/2 Q. C touches B. Then, because they are identical, the sum is 3/2 of Q, and it is divided into two pieces equally. So 3/4. For B and C shares the charge of a 3/2 into 3/4 evenly. The electrostatic force, original electrostatic force between A and B, according to the shell theorem, this is F capital Q squared divided by large D squared. Now we assume that A and B are of equal distance in comparison with the initial condition. Then the only difference is the change in the charge in A and B. The charge in the final state A and B is 1/2 of Q and 3/4 of Q. Substituting these values, you will find in comparison with the initial value, we have factor of 3/8. Number 13. Particle 1 with charge Q1 is positive, and particle 2, Q2, still positive charge is placed on minus D2. And D1 and D2 are positive value. Alright. The net force, on the x-axis with particle 1, okay, these two coordinates. The net force on another charge, Q, placed at the origin. There is a Q. Vanishes. The force on charge Q due to Q1. Alright. The relative direction from Q1 to this particle is in this direction. If they are both positive, the force must be repulsive. First assume Q1 and Q2 are positive, both positive. Yes, they are all positive. And we do not know the sign of Q, so temporarily we just put it Q is positive. It's not definite, but just temporarily. We assume. And the force applied on Q due to Q2 must be along this direction if both of them are positive. Because the two forces vanishes, that means the strength. If you consider the strength, the magnitude of the two force magnitude of two forces, the magnitude of two forces must cancel. Alright, so we can read the direction. This is toward left hand from the positive to the origin. So this direction is the unit vector is proportional to minus I. The magnitude is K product discharges product and distance d1 square. Okay, so minus I. The force on the charge Q due to Q2 is as written in here. This direction is plus I hat. The magnitude is in a similar manner. The distance is d2. This one should be d2. and product of two charges, Q and Q2, electrostatic constant K. Alright, so according to the superposition principle, we add these two forces together, F1 and F2, and we have negative sign and positive sign. They must cancel. So this one should vanish. This one is 0 because it is impossible to have K, Q. They are non-vanishing, and I hat is non-vanishing, so only this vector can vanish. The result is Q2 divided by D2 squared subtracted by Q1 divided by D1 squared must be 0. That leads to this equation. In the Rutherford model of the hydrogen atom, a proton of mass mp and charge E, we use E is a unit electric charge that is positive value. Is the nucleus, proton is the nucleus, and an electron, mass me, charge minus E, electron charge is minus E, moves around the proton in a circle of radius r. This is not true, but a good approximation. The Coulomb force constant K is approximately 9.0 times 10 to the 9 Newton meter squared per Coulomb square. The universal gravitational constant G is given in this way. Elementary charge E is given 1.6 times 10 to the minus 19 Coulomb. Masses of the proton and the electron are given by. We find the electrostatic force and the gravitational force. Substitute them, these constants. If we substitute these two, and we find the ratio of the electrostatic force and gravitational force between the proton and electron, you find the electrostatic force is much greater than the gravitational force. We expect that the gravitational force is very strong only if the particles are very massive, such as a celestial body. But normally, the very tiny objects, just like fundamental particles, gravitational force is very weak in comparison with the electrostatic force. Next, we considered elementary charge. Elementary charge is this one. You do not have to memorize all those digits, but at least you must remember 1.6 10 to the minus 19 Coulomb. But anyway, this is an exact value. It is not an approximate value, it is an exact value. And electron's charge is minus of this charge. Proton's charge is positive value itself. And neutron's charge is 0. Any charge is a multiple of these charges. So we call this as elementary charge, fundamental charge. Therefore, it is not a general real number. It is a multiple, integral multiple of this number. However, the size of this charge, unit charge, the elementary charge, is so small, we can make an approximation that we can treat it a kind of real number. But it is physically, the ideal mathematical system is not the case. So, for example, this tiny number that is smaller than the elementary charge, this number is smaller than the elementary charge. Therefore, it is impossible to have a particle, have a mass, have a charge less than the elementary charge. For example, this one, impossible. However, this is possible because proton is a sum of UUD, up quark 2/3, up quark 2/3, and down quark minus 1/3. If you sum them up, electric charge of proton is 0. Neutron is composed of UDD, up quark, down quark 1/3, minus 1/3. There are 2 down quarks. If you sum them up, then you'll find neutron is electrically neutral. Alright. This one shows that atomic reaction, the nuclear reaction formula. Beryllium is hit by a neutron. That means 2 alpha particles and 2 neutrons. Beryllium is an element with the symbol Be and atomic number 4. Atomic number 4. There are 4 protons. That means that there are 5 neutrons in here. So on the left side you have 5 neutrons, another neutron, so 6 neutrons. We have 4 protons, 2 protons multiplied by 2, so 2 by 2, so you have 4 protons. And in here, helium has the 2 neutrons. So 2 by 2, 4 neutrons in helium, 2 helium nucleus. You add up additional 2 neutrons, so you end up with 6 neutrons. So left hand side, right hand side, number of neutrons and number of protons are the same separately. The single isotope, this nucleus is called the alpha particle. Conservation of charge. We have assume that any matter consists of nucleus. Nucleus is either proton or neutron, and hadrons such as the neutron and proton are composed of quarks. And outside the nucleus, an atom is composed of the nucleus and electrons. And they communicate with each other through electromagnetic force, and the carrier of the electromagnetic force is actually the photon. So in elementary particle physics, we express such kind of process: electron and positron. Electron is a particle, and we put negative sign on top of the right side of the E plus. So it's called the positron. Positron is the same as electron, except that the electric charge is positive instead of negative. So these two particles are antiparticles. Antiparticles, that means that if they collide, they disappear. They become electrically neutral particle if they annihilate. This is annihilation process. Electron and positron meet together. The net charge is 0. They can convert into 2 photons. This is not a single process, but it is allowed. E plus and E minus annihilate the photons, 2 photons. It is this kind of process allowed. So this is called the pair annihilation. In this pair annihilation, net electric charge from the initial state and total electric charge in the final state, they are the same. 0 equals 0. Pair production. For example, electron-positron pair collide together to make a single photon, and they recreate electron-positron pair. This kind of process is called pair production. Even in the high energy elementary particle physics, the conservation of electric charge is so fundamental, is always true. We can solve the following problem with the knowledge we have already acquainted with. Similar applications are listed. So remaining part of this lecture, I will summarize mathematical formulas that are frequently used in this class. First of all, derivatives. The velocity is the time derivative of displacement vector. We have additional derivatives in the future. Basically, derivative is defined by this limit of this ratio. Function f given value of x, we have positive, infinitesimally small positive epsilon. So we have x plus epsilon. It is on the right side. So difference x plus epsilon. At this point, this is f of x. So the difference between f of x plus epsilon minus f of x divided by this small positive number. And we take the limit, epsilon goes to 0. We find this is the right derivative. If we do the same job on the left side, this is a left derivative. Derivative exists when the left derivative is the same as the right derivative. Very simple derivative. X derivative of x is 1. Trivial problem. We have multiple functions, the product of n functions. How can I take the derivative? You can do this with this formula. For example, product alright, ABC, then ABC, ABC, ABC. In such a manner, if you have a product of functions, you can find the derivative of this function. Applying this method, you can apply this to find the derivative of a polynomial. And you can apply the chain rule to find the result for not only a polynomial function, but also a polynomial function, composite polynomial function. Okay, what happens to the log function? Log function derivative, we use the same definition for the derivative. So if we subtract log x plus epsilon minus log x, the ratio gives a log 1 plus epsilon over x. And here this is epsilon, but we can use the same thing, epsilon over x, and multiply x. These two are the same. Then we need to find the limit of this, except that this x is factored out in front. One over x can be shifted to a power of 1 over epsilon in here, but it is trivial to find that this is definition of a Euler's number, sometimes called natural exponent, and log e equals identically 1. Hence, the final result is 1 over x, derivative of log x, 1 over x. Next, we consider exponential function. Exponential function, we use the definition of exponential subtraction of these two factors, two terms, and we factor out this common factor and end up with this expression with limit delta goes to 0 as well as epsilon goes to 0. Finally, that is closely related to this one that we already proved, the expression that this is related to the inverse derivative of inverse function. Hence, the derivative of exponential is always exponential. Next, we consider the derivative of x of a, x to the a, and where a does not have to be an integer. It can be a half integer or any real number. For simplicity, we consider the case x is a positive definite. We will find in a straightforward manner the xa derivative can be expressed as x to the a minus 1. This is just like the same. That is very similar. That is identical. The expression itself is identical to the polynomial derivative. But one should be very careful. And then you should be acquainted with Taylor series expansion. And I assume that you are very familiar with this expression. Taylor series expansion of the exponential function, Taylor series expansion of a sine function and cosine function, and log function. So Maclaurin series is a Taylor series expansion about x equals 0, and let me consider the Maclaurin series in about x equals 0. So the log 1 is identically 0, so it's not a good idea to expand log x. Instead, it's good to expand the log function as a log 1 minus x or 1 plus x. And you must be familiar with the expansion of this Taylor series expansions listed on this page. Very, very important in physics and many other fields. And in physics, especially from the next chapter, we will frequently use binomial expansion, and binomial expansion is just simply the direct application of Taylor series expansion for the power function whose power is not an integer. So let me summarize everything in here. You can make a Taylor series expansion of this, and in here, absolute value of z, this one can even be a complex number. This number, absolute value of this z must be less than 1. Must be less than 1. And the expansion can be made in such a manner. And this one can be obtained by making use of this derivative formula repeatedly. And you must memorize everything altogether, but you don't have to memorize all these factors, but at least you must be able to compute at least the first 3 terms, and in principle you can extend to any, but you have to memorize this and you have to reproduce by hand expanding this calculation. And binomial expansion for these two kinds are also useful in the future. And we have later we will study Einstein's relativity, and you will frequently find the Lorentz factor gamma. Lorentz factor gamma is defined by 1 over square root 1 minus beta squared, and this beta is velocity of a particle divided by the speed of light. And this expansion appears many times. In addition, in relativity, you'll find that energy of particle is rest mass m c squared, where c is the speed of light, squared plus p squared c squared squared. And if momentum p is very small, then we can make a non-relativistic expansion. Non-relativistic expansion that can be done by applying binomial theorem. Again, you must be able to expand at least 3 terms. Do not memorize simply, but you must be able to expand by hand. Next, we consider partial derivative. In physics, the functions are multivariables. It should be time dependent. It should be coordinate dependent, x, y, z. So time dependent and coordinate dependent. Though you have 4 variables, and the many cases you have to take the derivative with respect to a single variable, either x, y, z, or t, keeping any other variable the same. Okay? So the partial derivative, you must be acquainted with the partial derivative. So definition of partial derivative is exactly the same as a normal derivative, except that partial derivative with respect to x1 means vary x1 only and keeping the remaining variables the same. For example, in n-dimensional Euclidean space, the magnitude of a vector is the square root of x1 squared through xn squared. The partial derivative with respect to xi can be computed in this way. So partial derivative, and this one is x vector magnitude. If we take the partial derivative with respect to xi, then first we make use of chain rule to find this vector square root of a, because a 1/2. So okay, and applying chain rule. This one is this. So you must be familiar with this kind of calculation, because we frequently do this calculation in the future. Rotation matrix. At the end of in the previous class, we have considered the rotation of unit vectors in the xy plane, coordinate transformation xy, to x prime, y prime, and this is the result. And you had better follow up all this matrix calculation. Should be familiar with this. So the rotation matrix is multiplied many times. The style is the same. The only change is the shift in the parameter. You do not have to understand Lorentz transformation at the moment, but at least you can follow the mathematics. The structure is almost the same, except that sine, cosine, and sine hyperbolic, cosine hyperbolic. This is the rotation in the Euclidean space, and this is the rotation in Minkowski space that is related to special theory of relativity. You can click perhaps you must be familiar with linear algebra, but if it is not the case, you had better to understand how to compute the inverse matrix and determinant of a matrix and basic idea of linear algebra. You do not have to take the whole course of linear algebra. Instead, you just follow the simple calculation at the end of this lecture, because in our class we will frequently use this matrix algebra. Again, you can click it does not appear in my presentation notes, but in your computer you can click this hypertext, then you will find a reference appears, and read it through how to compute the inverse matrix and how to compute how to solve a very simple linear algebraic equation. Alright, so today we have studied elementary concepts involving the Coulomb's law, and at the end of the class we have studied some mathematical formulas. I hope you can follow because my mathematical formulas presented in here is very simple. You had better not to simply memorize, but to follow all the detailed calculation, because it will appear in this class as well as in your major other classes too. Derivative of exponential function, log function, polynomial function, applying chain rule, and Taylor series expansion. Right. Applying the Taylor series expansion to exponential, cosine, sine, log 1 minus x, and polynomial function, and function with power function that is always replaced with the logarithmic function, and applying this method to find the binomial expansion. And partial derivative will appear when you compute the electric field frequently. And I hope you must be familiar with the matrix calculation as far as the 2x2 and 3x3 inverse, and find the answer for the linear equations. Okay, that's it for today.